Right now, wherever you are, your whole world probably feels solid enough. The bed beneath you holds you up. The room around you seems still. The air feels like empty space. And the light, if there's any, seems soft and smooth, as if it simply pours itself across walls and blankets without effort. It feels natural to imagine that reality is made of things that stay where they are, move along clear paths, and quietly continue being themselves, whether anyone is watching or not. And yet, hidden inside the light on your ceiling, the screen in your hand, the atoms in your skin, and the tiny currents moving through the wires around you, there's a set of rules that does not behave that way at all. The strange part is not just that the world is more complicated than it looks. The strange part is that, at its smallest scale, the world seems to resist the very kind of common sense our minds are built from. Tiny things do not simply sit in one place like tiny pebbles. Light does not act only like a smooth wave. Energy does not always flow like water from a tap. Nature, when examined closely enough, begins to answer us in pieces, in chances, in patterns, in maybes. And tonight, that is the journey we are taking together, not into quantum physics as a pile of intimidating words, but into the slow story of how ordinary intuition kept failing, and how some of the smartest people who ever lived were forced, step by step, to accept a picture of reality they did not even like. This matters more than it may seem. Your phone works because of it. Modern clocks keep time because of it. Lasers, transistors, MRI machines, computer chips, solar cells, and much of the modern world stand on discoveries that once sounded impossible. Even more astonishing, those discoveries began not with wild speculation, but with embarrassment. Nature kept giving the wrong answers to the old rules. Hot objects glowed the wrong way. Light hit metal the wrong way. Atoms should have collapsed, but did not. Tiny things behaved like both waves and particles, depending on how you asked the question. So let's move slowly. You do not need to force yourself to memorize anything. You do not need to hold every idea tightly. Just let the story arrive one piece at a time, and by the end, what once felt like a famous fog of confusion may begin to feel like something softer, stranger, and much more understandable. For a long time, people believed physics was nearly finished. By the late 19th century, there was a real sense, especially among European scientists, that the great machine of nature had mostly been understood. Isaac Newton had explained motion and gravity. James Clerk Maxwell had united electricity, magnetism, and light into one elegant set of equations. Engineers were using physics to build telegraphs, railways, steam engines, and electrical systems. The world seemed orderly. If you knew where things were, how fast they were moving, and what forces acted on them, then in principle you could predict what would happen next. The universe, in this picture, was like a grand clock. Complicated, yes, but understandable. A stone thrown through the air followed a path. A planet orbited the sun. A beam of light traveled as a wave. Causes led to effects. The rules were firm, and what could not yet be explained was often assumed to be only a matter of patience. That old picture was powerful because it worked so beautifully for medium-sized things. It described cannonballs, bridges, falling apples, tides, circuits, and planets. It explained a world the human beings could touch, see, and build with. But here's the problem. Nature is under no obligation to make the smallest things behave like slightly smaller versions of the biggest ones. That was the hidden assumption, and for a while it went unnoticed. If a big object has a place, then surely a tiny object has a place too. If energy can be turned up smoothly, then surely it comes in a smooth stream. If light is a wave, then surely it is just a wave. These seemed like harmless assumptions. They felt obvious. But one by one, nature began to reject them. The first crack appeared in something that sounded almost ordinary. Heat and light. Imagine a metal object heated in fire. As it grows hotter, it glows. First dark, then red, then orange, then whiter and brighter. This seems simple enough. Hot things glow. But once physicists tried to predict exactly how a hot object should glow at different colors, the math went badly wrong. According to the best classical rules available, a perfectly heated object, called a blackbody, should release more and more energy at higher and higher frequencies. If you followed the old equations all the way, they predicted something absurd, an infinite amount of energy pouring out at the high-frequency end. This disaster later became known as the ultraviolet catastrophe, and the name fits because it was not a small correction. It was a collapse. The rules that had worked so well elsewhere had walked straight into nonsense. Now, think about that for a second. The crisis did not begin with scientists trying to sound mysterious. It began because hot objects in the real world were behaving sensibly, while the trusted math was behaving like a broken machine. Max Planck, a German physicist, stepped into this problem in 1900. He did not set out to overthrow reality. In fact, he was cautious by temperament and deeply committed to orderly physics. What he wanted was simply a formula that matched the glow of heated objects. And in the process of trying to save the situation, he made a move so strange that even he first treated it almost like a mathematical trick. He proposed that energy was not exchanged in a perfectly smooth flow. Instead, it came in little packets, little chunks, later called quanta. Not any amount, but specific amounts. A helpful picture here is a staircase instead of a ramp. In everyday life, we usually imagine energy as something you can increase smoothly, the way you can slowly pour more water into a cup. Planck's proposal said that, in some situations, nature behaves less like a ramp and more like steps. You cannot stand halfway between two steps in the same way. You land on one level or another. Or imagine a vending machine that will not accept any random scrap of metal. It only takes certain coins. That was the shocking suggestion. The tiny exchanges of energy between matter and radiation were not continuous. They were allowed only in fixed units related to a new constant of nature, now called Planck's constant. With that move, the bad prediction vanished. The glow of hot bodies suddenly made sense. But this did not yet feel like a new universe. At first, Planck himself did not fully believe that reality truly came in chunks. He had found a way to make the numbers work, and sometimes in science that happens before anyone understands why. This is one of the most important feelings to keep in mind as we move through quantum physics. The theory worked long before people agreed on what it meant. That emotional tension is part of the story. Again and again, the equation succeeded first, and the human understanding limped behind. Planck had placed the first crack in the old wall, but the wall did not fall at once. It shuddered, it held, and then another blow came. In 1905, Albert Einstein, still a young patent clerk with a mind full of impossible clarity, took Planck's idea and made it much harder to ignore. There was another puzzle at the time called the photoelectric effect. If you shine light onto certain metals, electrons can be knocked free. Classical wave theory suggested that brighter light should hit harder, the way a bigger wave might shove a boat more strongly. But experiments showed something odd. Sometimes brighter light failed, while dimmer light of a higher frequency succeeded immediately. It was not mainly the amount of light that mattered. It was the color, or more precisely, the frequency. Einstein's answer was daring. He said the problem makes sense if light itself sometimes behaves not just like a spread-out wave, but like little packets of energy. Not smooth water, but rain. Not a continuous wash, but tiny pellets, each carrying a particular amount of energy, depending on frequency. If a single packet did not carry enough energy, then no amount of weighting or piling up brightness would free the electron. But if one packet crossed the threshold, the electron could be released at once. This was a deeper wound to the old worldview than Planck's original move. Planck had quantized the exchange of energy between matter and light. Einstein was saying that light itself comes in quanta. Later, these would be called photons. And this is where the story becomes beautifully uncomfortable. Light had already behaved so convincingly like a wave. Interference patterns, diffraction, and Maxwell's equations all pointed that way. So now physicists faced a growing contradiction. Was light a wave or a particle? The answer that slowly emerged was not the comforting one. It was not that scientists had simply picked the wrong picture. It was that both pictures captured part of the truth, and neither one alone was enough. Light was beginning to act like something that could not be neatly folded into the categories human beings preferred. If that were the only confusion, quantum physics would already be strange enough. But the trouble kept spreading. Attention turned to the atom. By the early 20th century, the atom was no longer just a philosophical guess. J.J. Thomson had discovered the electron in 1897, and Ernest Rutherford later showed that atoms contain a tiny, dense, positively charged nucleus. The simplest mental image was a tiny solar system, electrons orbiting the nucleus the way planets orbit the sun. It sounds neat. It feels intuitive. Small things circling a center. The trouble is that according to classical physics, a charged particle moving in a curved path should radiate energy. That means an electron in orbit should constantly lose energy, spiral inward, and crash into the nucleus. In other words, atoms should be unstable. Matter itself should collapse. But matter does not collapse. You do not dissolve into electromagnetic tragedy while lying there. Tables do not vanish. Air does not fail. The world persists. So once again, the old rules were producing a result that reality refused to obey. Niels Bohr, a Danish physicist with a remarkable ability to think boldly inside confusion, offered a rescue in 1913. He proposed that electrons and atoms are allowed to occupy only certain specific orbits, and while in those allowed orbits, they do not radiate energy. Only when an electron jumps from one allowed orbit to another does it emit or absorb light, and the energy of that light matches the gap between the two levels. This was another staircase idea. The electron could not live anywhere it pleased, any more than a person walking upstairs can place both feet halfway between steps and call that a resting place. Allowed levels, forbidden levels, stable states, sudden jumps. Bohr's model was strange, but it explained something important. The spectral lines of hydrogen. Instead of emitting every possible color, hydrogen emitted very specific colors. Bohr's quantized orbits accounted for that. The model was elegant and useful. It saved the atom from collapse, at least on paper. But here's the thing. Bohr's picture also felt like a patch. Why those orbits? Why those jumps? Why should nature allow some paths and forbid others? The model was powerful, yet incomplete. It worked especially well for hydrogen, but not cleanly for more complicated atoms. It was like finding a bridge that held long enough to cross a river, while still hearing the timbers creak beneath you. The old classical world had clearly failed, but the new quantum world was arriving in pieces, and no one yet had the full map. What came next was one of the most remarkable shifts in all of science, because it required physicists to stop imagining matter as tiny little marbles. In 1924, a young French physicist, Louis de Broglie, asked a reversal of Einstein's question. If light, once thought to be a wave, could also behave like a particle, then perhaps matter, usually thought of as particle-like, might also have wave-like properties. It was a breathtaking act of symmetry. Maybe the universe was not divided neatly into wave things and particle things. Maybe both matter and light carried a strange dual nature. This idea sounds airy at first, but it became concrete very quickly. If electrons have wave-like properties, then some mysteries begin to soften. A wave can form standing patterns, the way a string can vibrate only in certain stable modes. That offered a deeper way to think about Bohr's allowed orbits. Perhaps electrons are not tiny planets following little tracks at all. Perhaps the stable states and atoms exist because matter, at that scale, behaves like a wave that can fit around the nucleus only in certain allowed patterns. Suddenly, the atom no longer needed to be forced into a miniature solar system. It could be something much stranger and, in a way, more natural. Soon after, Erwin Schrödinger developed wave mechanics, and quantum theory took a giant step forward. Instead of trying to describe electrons as little dots moving around like microscopic billiard balls, physicists now used a mathematical object called the wave function. This is one of the most important and confusing ideas in quantum physics, so let's stay here for a moment. The wave function is not quite a physical wave in the ordinary sense, like a water wave sloshing across a pond. It is more like a description of possibilities, a structured cloud of what might happen. From it, you can calculate the probabilities of finding a particle in different places or states. It tells you how the maybes are arranged. A gentle way to picture this is to imagine a dark room where a firefly is not directly visible, but a glowing mist shows where it is likely to be. The brighter the mist in one region, the more likely you are to find a firefly there when you look. It is not perfect, but it is closer than imagining a tiny marble on a tiny track. In quantum mechanics, before measurement, the theory does not always give you one definite answer like, the electron is exactly here. Instead, it gives a spread of possibilities with different weights. The electron is described by a wave function, and that wave function evolves smoothly according to Schrödinger's equation. Then, when a measurement occurs, a definite result appears, and that turns out to matter more than anyone expected, because it changes what we mean by knowing something. In classical physics, uncertainty is usually a sign of ignorance. If you do not know where a ball is, that may simply mean you have not looked carefully enough. The ball itself still has a definite place and speed. But in quantum physics, the uncertainty seems to be more fundamental. The theory does not merely hide values from us. In many cases, it tells us that the world at that scale is not arranged in the old definite way to begin with. This becomes especially clear in the uncertainty principle, introduced by Werner Heisenberg in 1927. The common rough version says that you cannot know a particle's exact position and exact momentum at the same time. The more precisely one is defined, the less precisely the other can be. People sometimes hear this and imagine it is just because our tools are clumsy, as if tiny particles are too slippery for our microscopes. But that is not really the heart of it. The deeper point is that a perfectly sharp position corresponds to a wave spread made from many different wavelengths, and a perfectly sharp momentum corresponds to a clean wavelength spread through space. The two demands pull against each other. Nature does not let you have both in full. Imagine trying to create a musical note that is both perfectly pure and confined to a single instant. A pure note wants duration. A sharply localized instant wants a blur of frequencies. Quantum uncertainty is a bit like that, though again, only a bit. It is not a statement about laziness or bad instruments. It is built into the wave-like structure of matter. This is why quantum physics feels so unsettling. It does not merely say, "You have not measured carefully enough." It says, "The old question may not have the kind of answer you expected." Now we come to one of the most famous and haunting experiments in science, the double-slit experiment. You may have heard it mentioned in a dramatic tone, but its real power lies in how cleanly it exposes the new rules. Imagine a barrier with two narrow openings in it and a screen behind it. If you send waves through the openings, like ripples in water, the waves spread and overlap, creating an interference pattern, bands where they strengthen and bands where they cancel. If you send ordinary particles, like tiny pellets, you expect them to go through one slit or the other and form two piles on the screen. Straightforward enough. When scientists send quantum objects, such as electrons, one at a time, what happens is astonishing. Over time, the impacts build up not into two simple piles, but into an interference pattern. It is as if each electron behaves like a wave passing through both slits and interfering with itself. And yet, when it lands on the screen, it appears as a localized hit, like a particle. So what is it doing in between? Not a simple wave, not a simple particle. Something that produces wave-like probabilities and particle-like detections. The really unsettling part comes when you try to watch which slit the electron goes through. If you place a detector to find out, the interference pattern disappears. The result changes depending on whether the path information is available. When unwatched in that specific way, the electron behaves as if both routes matter together. When watched, it behaves more like it chose one. This is why so many people say quantum physics feels like hide and seek with reality. The answer you get depends on how you ask the question. Observation is not always a neutral peek through a window. At this scale, the arrangement of the experiment helps define what kind of outcome the world can produce. Now we should be careful here. Quantum physics does not mean that human consciousness magically creates reality by staring at it. That is a popular oversimplification. In most physics discussions, measurement means an interaction that records or makes available information in a definite way, not necessarily a person using their mind like a spell. Still, even after that clarification, the situation remains strange. Reality at small scales does not seem to carry a full set of classical answers quietly hidden in a box, waiting for us to open it and read them off. The act of measurement is not just finding out. It plays a constituting role in the kind of result that appears. This brings us to superposition, one of the central words in quantum physics. A superposition is a combination of possible states. If that sounds abstract, let's make it gentler. In the classical world, we imagine a coin as either heads or tails, even before we look. In the quantum world, a system can be in a state that is not simply one or the other in the old sense, but a meaningful combination that can produce different outcomes with specific probabilities when measured. This does not mean the object is just secretly undecided in the way a person might be undecided between tea and coffee. It means the theory describes it with a structure richer than the single classical choice. The temptation is to say, so the particle is in two places at once. Sometimes that is a useful doorway, but it can also mislead. Better to say that the quantum state can encode multiple possibilities that later yield one definite outcome when measured. The wave function carries those possibilities in a mathematically precise way. Interference effects show that the possibilities are not like separate classical guesses sitting side by side. They interact like waves. That is what makes quantum superposition so powerful and so hard to picture. It is not ordinary uncertainty. It is a new kind of description altogether. This is also the reason atoms are not just little solar systems with tiny orbiting balls. In quantum mechanics, an electron in an atom is described by a wave function spread through space. The famous atomic orbitals are not neat planetary tracks. They are patterns of probability, regions where the electron is more likely to be found. If you have ever seen those fuzzy cloud-like images of atoms, those are attempts to show the maybe cloud. And in a way, that cloud is one of the gentlest visual metaphors in all of quantum theory. The electron is not merely lost. It is described differently. Nature, at that scale, is not organized as tiny hard beads following crisp lines. As the theory developed in the 1920s, a philosophical struggle opened up. On one side stood Niels Bohr and others who leaned toward what became known as the Copenhagen interpretation. Different versions of this view exist, but at its core was an attitude of disciplined humility. Quantum mechanics, they argued, does not necessarily give us a picture of tiny objects doing classical things behind the scenes. It gives us a framework for predicting measurement outcomes. The theory works. It tells us what can be said, what can be known, and with what probabilities. Demanding an old-fashioned visual story underneath may simply be asking nature to be something it is not. Einstein was never fully satisfied with that. He helped create quantum theory, yet he resisted the idea that probability and indeterminacy were the deepest layer of reality. He wanted a world that existed in a more definite way, whether we observed it or not. His famous line, often shortened to "God does not play dice," was not a complaint about religion, but about the role of chance in fundamental physics. Einstein suspected that quantum mechanics might be incomplete, that hidden details might someday restore a deeper order underneath the probabilities. This disagreement was not just a technical dispute. It was a wound in the old picture of reality. What counts as explanation? Is it enough for a theory to predict outcomes perfectly, even if it refuses to provide the kind of visual mechanism our minds prefer? Or should we keep searching for a more complete story behind the numbers? Quantum physics forced scientists to confront not only new facts, but new limits on what it means to understand. That is one reason it still feels emotionally alive. The confusion is not a side effect. It is woven into the subject to sharpen the problem. Let's step into one of the most famous thought experiments ever invented, Schrödinger's cat. Erwin Schrödinger designed it in 1935 not to celebrate quantum weirdness, but to expose how disturbing the standard picture seemed when extended to everyday objects. Imagine a sealed box containing a cat, a tiny radioactive atom, a detector, and mechanism that releases poison if the atom decays. Quantum theory says the atom can be in a superposition of decayed and not decayed before measurement. If the microscopic event is linked to the cat's fate, then before the box is opened, is the cat somehow in a superposition of alive and dead? The point is not that anyone literally wants to treat cats this way. The point is that the quantum rules, when naively scaled up, produce a picture that feels absurd. So where does the transition happen? When do fuzzy quantum possibilities give way to the definite world we live in? Does the wave function really collapse? If so, what causes the collapse? Is it measurement, environment, information, or something deeper? These questions are not signs that quantum mechanics failed. The theory keeps working, but they show that our interpretation of the theory is still unsettled. One important development here is the idea of decoherence. Without turning it into a wall of jargon, the rough idea is that quantum systems do not stay isolated very easily. They interact with their surroundings constantly. Those interactions spread quantum information into the environment in ways that suppress certain interference effects. This helps explain why the large world looks so definite and classical most of the time. The delicate quantum patterns that are easy to preserve in carefully controlled experiments are usually washed out in ordinary life. A cat is not a lonely electron drifting in a laboratory setup. It is a warm, complex, noisy system entangled with air, light, molecules, and time itself. Decoherence is a powerful piece of the puzzle, but it is not the entire philosophical answer. It helps explain why superpositions become hard to observe at large scales. It does not by itself completely settle why one particular outcome is experienced. That lingering gap is part of why different interpretations of quantum mechanics still exist. Some physicists are content to use the theory and leave metaphysics aside. Others continue to search for a deeper account. And for our purposes tonight, it is enough to notice something simple and beautiful. Quantum physics works with extraordinary precision, even while its meaning remains a subject of real debate. Now let's turn to entanglement, because if superposition bends the mind, entanglement stretches it across space. When two quantum systems interact in certain ways, they can become linked so that the state of the whole system is well defined, even though the individual parts do not possess separate definite properties in the old classical sense. Later, if the systems are far apart and you measure one, the result you obtain is strongly correlated with the result for the other. Einstein called this spooky action at a distance, and you can feel why. It seems to suggest that reality is woven together more deeply than classical intuitions allow. A careful version is important here. Entanglement does not mean you can send an ordinary message faster than light just by measuring one particle. Relativity remains safe in that sense. But entanglement does mean that the joint state of the particles contains correlations that cannot be explained by a simple picture, in which each particle quietly carries its own complete list of local instructions from the start. This issue became much sharper through later work, especially Bell's theorem in the 1960s and experiments that followed. Those experiments strongly supported the quantum predictions and ruled out broad classes of hidden variable explanations that obey certain classical assumptions about locality and realism. The deeper emotional lesson of entanglement is not that the universe is magical in a lazy storytelling way. It is that our ordinary notion of separateness begins to fray at the quantum level. We like to imagine the world as built from little self-contained units with their own private properties. Entanglement says the whole can carry information that is not reducible to the old picture of independent parts. The relation matters. The system matters. Reality, at least in these circumstances, is not just beads on a string. It is a pattern that sometimes belongs more to the connection than to the individual pieces. This is why quantum physics can feel both simple and impossible. On one hand, many of its equations are compact. On the other hand, the world they describe refuses to fit neatly into the visual habits we learned from chairs, stones, rain, and windows. Our brains evolved to handle medium-sized objects moving at medium speeds under everyday conditions. We are not naturally equipped to picture electrons, wave functions, or entangled states. That does not mean the subject is nonsense. It means our intuition was trained for a different arena. Think of it this way. A fish might build perfect common sense for water and have none for deserts. A human mind builds powerful common sense for warm, visible things at ordinary scales. Quantum physics lives far below that zone. So confusion, in this case, is not failure. Confusion is often the correct emotional response to a reality deeper than the one our nervous systems were designed to navigate. That is a comforting thought, in a quiet way. You are not bad at quantum physics because it feels odd. Quantum physics feels odd because it is odd. Still, the oddness is not random. This matters. Quantum mechanics is not a bag of whimsical paradoxes thrown at the wall of science. It is a tightly structured theory with rules, symmetries, operators, amplitudes, and astonishing predictive power. Physicists can calculate atomic spectra, chemical bonds, the behavior of semiconductors, and the dynamics of particles with extraordinary accuracy. So when people say quantum physics is weird, that should never be confused with saying it is sloppy. In fact, part of what makes it so haunting is how well it works. The rules are strange, but they are not vague. Let's make some of the central confusions even clearer by slowing down and naming them in ordinary language. First, energy is not always smooth. At small scales, many physical quantities come in discrete steps. Second, light and matter do not fit cleanly into separate boxes, called waves and particles. They show features of both, depending on context. Third, tiny systems are often described by probabilities and superpositions, rather than definite classical states. Fourth, measurement is not always a passive glance. It is bound up with the kind of result that becomes definite. Fifth, some pairs of properties cannot both be made sharply definite at once. Sixth, quantum systems can become entangled, linking outcomes across distance in ways that classical intuition resists. That may sound like a list, but I want you to feel the deeper thread, connecting all of it. Every one of those surprises grew out of the same larger lesson. The classical worldview kept assuming that the microscopic world was just the everyday world shrunk down. Quantum theory is what happened when nature kept refusing that assumption. So the subject is not strange because scientists wanted to make it so. It is strange because the world, when pressed at small scales, gave answers that broke the old categories. Quantum physics is the record of that break. Let's go back for a moment to something that often troubles people. If quantum theory is so probabilistic, does that mean nothing is real until observed? Not exactly. That slogan is too crude and can send the mind in the wrong direction. Quantum systems evolve according to very precise rules, even when no one is looking. The wave function changes lawfully. Experiments repeat with reliable statistical patterns. What is different is the structure of what is evolving and how definite outcomes appear. Many interpretations offer different accounts of what is really there between measurements. Some say the wave function is a real physical object. Some treat it as information or knowledge. Some suggest that all outcomes continue in branching worlds. Others propose hidden variables or spontaneous collapse mechanisms. You do not need to pick a camp tonight. The important thing is to notice that quantum mechanics is a complete working machine at the level of prediction, while still inviting deep disagreement about ontology, about what kind of reality the math is actually describing. That is unusual. In many subjects, once the math works this well, the conceptual picture also settles down. In quantum physics, the success came first, and the peace treaty never fully arrived. The many worlds interpretation, for example, takes the wave function very seriously and denies a special collapse. On that view, all the possibilities encoded in the quantum state continue, and what we experience as a single outcome is part of a larger branching structure. This can sound breathtaking or exhausting, depending on the mood you meet it with. Other physicists prefer hidden variable approaches, such as pilot wave theory, where particles do have definite positions guided by a wave. Others look toward objective collapse theories, where the wave function really does collapse physically under certain conditions. Each attempt is, in its own way, a bid to recover a story about what the world is doing. What makes this so fascinating is that these disagreements can coexist with the same experimental predictions in many ordinary cases. So even when the laboratory results are crystal clear, the meaning behind them can remain open. Quantum theory, in that sense, is like a map that gets you to the right city every time, while leaving philosophers arguing about what the landscape ultimately is. That is not weakness. It is part of the intellectual richness of the field. Now let's bring the story down from deep theory into the familiar world around you, because quantum physics is not sealed in a glass case. It hums through daily life. The electrons and atoms occupy quantized states, and that underlies chemistry itself. Why molecules form, why matter has structure, why the periodic table works the way it does, why substances behave differently from one another. All of that depends on quantum rules. The solidity of ordinary objects, strange as this may sound, is not just a matter of little hard balls touching. It involves quantum states, electron behavior, and exclusion principles that prevent matter from collapsing into a featureless heap. That exclusion principle, associated with Wolfgang Pauli, is another subtle but profound rule. Certain particles called fermions, including electrons, cannot all pile into the same quantum state. This one fact helps shape the architecture of atoms and the layered structure of matter. It is part of why chemistry has variety, why electrons fill shells, why stars and white dwarfs resist certain forms of collapse, and why the world has texture instead of complete sameness. So even when quantum physics feels slippery, it is also the reason reality has so much stable structure. Your computer chip works because electrons move through solids in ways quantum mechanics predicts. Semiconductors behave as they do because energy levels in materials form bands with allowed and forbidden regions. By carefully controlling impurities in those materials, engineers created transistors, the tiny switching elements behind modern electronics. Lasers depend on stimulated emission, a quantum process in which excited atoms release light in coordinated ways. MRI machines rely on quantum properties of atomic nuclei and magnetic fields. Atomic clocks, among the most accurate clocks ever made, use precise quantum transitions to measure time. GPS would drift badly without such clocks. So the same theory that baffled Einstein helps guide planes, phones, satellites, and hospitals. And there's something almost tender in that fact. A theory born from the failure of old certainty now quietly supports the ordinary routines of modern life. You set an alarm, send a message, take a photograph, look at a screen, trust a navigation signal, and the legacy of quantum confusion is already there, doing its work without asking for applause. The world did not become less usable when it became stranger. In many ways, it became more understandable, more fertile, more open to invention. That said, not everything is settled. Quantum computing, for example, has brought old ideas like superposition and entanglement into a new public spotlight. A quantum bit, or qubit, is not just a tiny classical bit that is either 0 or 1. It can exist in a superposition of states and can become entangled with other qubits. Under carefully controlled conditions, this allows certain kinds of computation to be performed in ways that differ radically from ordinary computing. It does not mean a quantum computer magically tries every possible answer in the childish sense people sometimes say, but it does use interference and superposition to process information in a distinctly quantum manner. Building such machines is hard precisely because the quantum world is delicate. The larger, noisier environment is always waiting to wash away the fragile patterns through decoherence. So in a beautiful twist, the very thing that makes quantum physics powerful also makes it difficult to harness. Engineers and physicists must protect the maybe cloud from the ordinary world long enough to do useful work with it. That ongoing effort is a reminder that quantum theory is not a historical curiosity. It is still unfolding into technology, still challenging design, still shaping the future. There are also mysteries at the frontier where quantum theory meets gravity. General relativity describes the large-scale structure of space, time, and gravity with stunning success. Quantum mechanics describes the small-scale behavior of matter and radiation with equally stunning success. But fitting them together into one fully coherent framework has proved extraordinarily difficult. Black holes, the early universe, and the nature of space-time itself all seem to press us toward a theory deeper than either framework alone. So even after a century of triumph, quantum physics remains unfinished at the edges. This should give us pause in the best sense. The theory is not a chaotic mess waiting to be cleaned up. It is one of the most successful intellectual achievements in history. And still, it leaves room for deeper synthesis. That combination, enormous power with unresolved foundations, is part of why it keeps pulling people in. It is not just a solved chapter in a textbook. It is an active borderland between clarity and mystery. Let's step back now and ask the gentlest version of the biggest question. If you were truly 5 years old, and someone asked what quantum physics says, what is the simplest honest answer? It might be something like this. The tiny world is not built the way your eyes expect. Tiny things do not always have one clear place, and one clear path at every moment in the old everyday sense. Light and matter can act like both waves and particles. Nature often gives possibilities first and definite answers later when measured. Some amounts come in little steps instead of smooth flows, and tiny things can stay connected in ways that do not feel local or separate the way large things do. But if you were a little older, maybe 10 or 15, or lying awake as an adult in the dark, we could add something even more important. Quantum physics does not tell us that reality is irrational. It tells us that our default visual logic is limited. We expect reality to behave like the world that shaped our ancestors. Stones, fruits, trees, weather, paths, animal tracks, day and night. Quantum theory says that beneath that familiar layer is a deeper grammar. It is lawful, measurable, and astonishingly effective, but it is not written in the language of everyday common sense. And that is why the story of quantum physics is really the story of humility. Again and again, human beings guessed that the universe should behave in the shape of their intuition. Again and again, at the smallest scales, the universe quietly said no. Not angrily, not dramatically, just firmly. Hot things glowed in ways old theory could not explain. Light knocked electrons loose in a way that depended on frequency, not just brightness. Atoms refused to collapse. Electrons produced interference, one at a time. Outcomes depended on experimental setup. Particles separated by space behaved as parts of a single quantum whole. Each surprise was a little correction to human certainty. There is comfort in that, if you let it settle. We often imagine understanding as the feeling of the world becoming more familiar, but sometimes deeper understanding feels like the opposite. It feels like realizing that reality is not obligated to resemble the furniture of your thoughts. Quantum physics widened the meaning of knowledge. It taught us that prediction can outrun visualization, that mathematics can hold truths the senses never prepared us for, and that the world may be clearer in structure than in picture. Even the famous phrase, explained like you are 5 years old, hides something wise. When people ask for that kind of explanation, they are not always asking to be talked down to. Often they are asking for honesty without fog. They are asking for the first clean handles. They want someone to say, here is the simple core, here is what breaks, here is what replaces it, and here is why that replacement matters. Quantum physics allows that, as long as we respect the edges. We can speak simply without pretending the mystery disappears. So let's gather the whole journey in one calm breath. First came confidence in a classical world of continuous energy, clear paths, and definite hidden properties. Then hot objects broke that confidence, and Planck introduced energy quanta. Then light itself broke the old rule, and Einstein showed that frequency mattered because light came in packets. Then the atom broke the planetary picture, and Bohr allowed only certain orbits and jumps. Then matter itself became wave-like through de Broglie. Then Schrödinger gave those waves a governing equation. Then Heisenberg showed that exact classical precision was not available in the old way. Then the double-slit experiment revealed that possibilities interfere. Then superposition and measurement forced new questions about reality. Then entanglement showed that separateness could fail. And through it all, the mathematics kept working, even when the meaning stayed unsettled. That is the dramatic engine underneath every confusing thing about quantum physics. Each solution solved a problem and opened a deeper one. Planck fixed radiation and broke continuity. Einstein explained the photoelectric effect and cracked wave intuition. Bohr saved the atom, but with rules that felt almost mystical at first. Wave mechanics explained more but dissolved the tiny marble picture. Measurement restored definite outcomes, but at the cost of easy realism. Entanglement rescued the predictions, while challenging locality and separateness. The theory did not become less successful As it became less comfortable, it became more successful. And maybe that is one of the quiet philosophical gifts of the subject. We're used to thinking that truth, when found, should feel soothingly intuitive. Quantum physics suggests otherwise. Sometimes truth feels like a pattern you can trust even before you can love it. Sometimes understanding begins not when reality becomes simple, but when you stop demanding that it match the wrong simplicity. In that sense, quantum theory is not just a science of tiny particles. It is a lesson in letting the world be more itself than our habits first allow. As you lie there, perhaps the room feels a little different now. Not less real. If anything, more richly real. The smooth wall is made of atoms whose electrons do not move like tiny planets. The darkness around you is crossed by photons. Your own body is a vast choreography of quantum-governed matter arranged into tissues, breath, memory, warmth, and awareness. The familiar world has not disappeared. It has simply become the surface of a much deeper order, one that does not announce itself directly to the senses, but is there all the same, holding together the very possibility of ordinary life. And perhaps that is the softest ending quantum physics offers. At the smallest scale, reality is not broken. It is only strange in a way our everyday minds were never built to anticipate. The confusion is real, but it is not a wall. It is a doorway. Behind it is a universe where certainty comes in patterns more than pictures, where possibility has structure, where the unseen is not empty, and where the tiniest things, far from being simple, carry a depth that the large world gently rests upon. So if some part of it still feels slippery, let that be okay. You do not need to grip the whole theory at once. You only need to notice the shape of the story. We thought the world was one way, and the small world kept answering otherwise. Slowly, patiently, reluctantly, human beings learned to listen, and in listening, they discovered our chaos, but a deeper kind of order, one that powers our machines, shapes our matter, confounds our intuition, and waits beneath the quiet surface of everything around you. Even now, as the room grows still, and the questions soften, and the strange, precise, beautiful maybe cloud of the universe carries on in the dark,